All right, welcome to the lesson on heating curves and phase changes. So what we're looking at here is a heating curve, and what we're going to be studying. So we got here on the x-axis we have plotted the energy added to our sample in kilojoules and the temperature. And our sample, by the way, is 36.03 grams of water, which also corresponds to 2 moles of water. So the first thing we want to look at is the scale that we're looking at here. So we're starting from negative 25 degrees Celsius, and we're bringing our sample up to 125 degrees Celsius. And along the way, a few things are happening. So there are some regions where energy is being added, and the temperature is increasing in this case because we're adding energy. And there are some segments like BC here and DE here that energy is still being added, but the temperature is not changing. And if you remember from class, what that means is under those conditions, that tells you there is a phase change going on at that time. So the first thing that I want you to do is take a minute to think about what is present in each phase or each segment line. How many phases are present and what are they? So keep in mind a couple of things. Remember that the flat parts are phase changes. So you're looking for 2 phases. And this is water, so the temperature range will tell you what phase you might expect when there's only one present. So hit pause, take a second, and think about this. So fill in, what the phases are for each little line segment. And here's what you should have got. So again, when the temperature is increasing, that tells you that you've got a single phase. So in this case, between negative 25 and 0 degrees, that's going to be a solid ice. Between 0 and 100 degrees, that's going to be liquid. And between 100 and 125 degrees, that's going to be the gas. Now in this flat segment here, DE, the temperature isn't changing. It's at 100 degrees, that's when it's boiling. So this tells you that it is liquid and gas that is present. Those are the 2 phases. And likewise at 0 degrees, in this case, you've got a phase change going on. The 2 that you've got in equilibrium at that time are solid and liquid. All right, so the next thing is we're going to figure out how much energy this entire process took. And the key is to break it up into steps of 2 types, because the way you handle the energy for a temperature change area where you've got one phase is very different than how you handle the energy when there's a phase change going on. So here's the information that you had given to you, that you've got the heat capacities of solid, liquid, and gaseous water. So remember, they're different, so be mindful of using the correct one. And this also gives you the enthalpy or the energy of fusion melting for water. So this tells you that it requires 6.01 kilojoules per mole of water to melt water. And likewise, it takes 40.1 kilojoules of energy to vaporize a mole of water. And the 2 equations that you're going to be using are right here. One tells you the energy involved in changing the temperature of something. So this is the calorimetry equation. And so the heat, so this could be delta H, it could be Q, it could be delta E, is just the mass times the heat capacity times the temperature change. And for the phase changes, it's just going to be the amount that you have, the number of moles, times the enthalpy change of that. So we're going to break it down into steps. And the first step is going to be just heating the solid to its melting point. So going from 25 below 0 to 0 degrees Celsius. And so this is a direct application or plug and chug of the calorimetry equation and just put the values in. So you were told that the mass was 36 grams. This is solid, so make sure you use a heat capacity of 2.09 joules per gram per degree Celsius. And also make sure you get the temperature range right. This is a common goof. It's not the entire temperature change, negative 125 to 125. It's just the temperature range of that segment, for which the final temperature is 0 degrees and the initial temperature was 25. So it's 25 minus negative 25, so the change in temperature is positive 25. And if you put all that together, multiply everything through, you get 1883 joules or 1.883 kilojoules. All right, so that's the first segment. The next segment was one of the flat ones, and it was a phase change, and that occurs at 0 degrees Celsius. Now, the first key that should tell you that this is not the proper equation is that in this case, there's no temperature change. So everything would be 0, which sort of should make you question that. So in this case, it is a direct application of this one. And what this little notation here says is that the enthalpy change, or the heat or the energy released in a phase change, is equal to the molar enthalpy of that phase change times how many moles you've got. So it's pretty straightforward. I've got 2 moles of water. The enthalpy of fusion is 6.01 kilojoules per mole, which means that to melt that water at 0 degrees Celsius is going to require 12.02 kilojoules of heat. And now we've done everything at least once. So now what we have is water at 0 degrees Celsius. So the next step is to heat that water from its melting point, 0, to its boiling point, 100 degrees Celsius. And again, this is just a straight plug and chug of the calorimetry equation. So what's going to be different? Well, one thing that's going to be different is the heat capacity of liquid water. And then the other thing is what the temperature range is going to be. Now in this case, you know that you are going the entire liquid range from 0 degrees to 100 degrees. So the delta T is a positive 100 degrees. And all that put together will give you a enthalpy change of positive 15.08 kilojoules. So that's how much energy it takes to take that water, that 36 grams of water, from 0 degrees Celsius at its melting point to its boiling point of 100 degrees Celsius. Now our final temperature was going to be 125 degrees, which means once we get the liquid up to 100, it's going to boil. So then we're going to use the heat of vaporization of water to figure out how much energy it takes to go from liquid water at 100 degrees Celsius to gaseous water or steam at 100 degrees Celsius. And that is a straight application of this equation. The only difference is you are using the enthalpy of vaporization this time and not the enthalpy of fusion. So I've got 2 moles. It costs you 41 kilojoules per mole of water to boil it, which means that this step is going to be 80.2 kilojoules. Now we only have one more segment left, and that is the range that went from 100 degrees to 125. So we're taking steam at 100 degrees and then heating it up to 125 degrees. So this one, so this was the last segment here, 100 to 125, is going to be another application of the calorimetry equation. And so the only difference here, just be mindful of the temperature range and the heat capacity. So you want the heat capacity for gaseous water, 1.84 joules per gram per degree Celsius. And then the temperature range, the final temperature is 25. The initial temperature was 100. And all that put together gives us a enthalpy change of 1.658 kilojoules for that last step, which was heating the steam from 100 degrees to 125 degrees. And that's pretty much it. So we have in sequence calculated the energy of this step, this step, this step, this step, and that step. And the overall energy is just going to be the sum of those. So the first step, taking ice from negative 25 to its melting point of 0, that was 1.9 kilojoules. Second step, melting the ice, that was 12 kilojoules. Third step, taking the liquid water from 0 degrees to 100 degrees, that was 15 kilojoules. Third step, taking the 100-degree water and boiling it, and turning it into 100-degree steam, that was 80.2 kilojoules. And last but not least, taking the 100-degree steam, heating it to 125-degree steam, that was 1.7 kilojoules, for a total of 109.10 kilojoules. And if you look at my graph, that's actually about where it stops. So Everything was actually about where it's supposed to be. And again, I also want to point out that especially because of the hydrogen bonding in water, it has a phenomenally high heat of vaporization. This is a very uncommonly high vaporization. And that in going from all the way from -25 to 125 degrees Celsius, 73% of the energy needed to do that is this one step here, vaporizing it. All right, so that's pretty much it. So rewind and listen to this as much as you like. I want to point out there's a couple of things. If you're thinking about what the exam question might look like or what a quiz question is going to look like if you haven't seen the quiz yet. I might not necessarily give you a temperature range that involves 2 phase changes. I might just give you one. So be mindful of the temperature ranges you're working at. On the exam, I would probably give you one that has at least 1 phase change in it though. If it's something other than water, I would give you what the temperatures are and what the enthalpies of vapor, what the enthalpies are and what the heat capacities are. So just be mindful of those temperatures and see that if I give you a range that you can see if there's a phase change in that range. So your exam question might not have 5 steps. It might have 2, it might have 3, or something like that. So be mindful of the temperature range. And the other common thing is that break each of these temperature change steps down to the appropriate range. So the temperature, this example had an overall temperature change of 150 degrees, but you need to break it up into a 25-degree temperature change, a 100-degree temperature change, and then another 25-degree temperature change. So be mindful of that. Good luck on the quiz and on the exam, and I will see you on Tuesday.